Hi. Today we look at a method called shooting method. We use this method to solve boundary conditions, boundary value differential equations. So for example, if you have equations such as this, t square if you have one which goes like this, t square y by dx square plus e raised to minus xy plus sine of dy by dx. If you have a ordinary differential equation such as this with boundary conditions y of y of 1 equals 0 and y of 2 equals 0.5. So this problem is defined within a one-dimensional domain which goes from 1 to 2 in the x direction with boundary values equal to 0 and 0.5 at the two ends of the domain. So till now we have looked at techniques which can solve initial value problems. If you remember, we saw Ode45, and there are also other methods like Euler method and Ramikutta method. But this is a problem in which we need to solve a boundary value problem. So the way the shooting method works is that you can convert this boundary value problem to a initial value problem, and you solve for the you start from one boundary and you solve your equation so that you reach the value at the other boundary. So you shoot with different guesses until you eventually reach the value at the other boundary, right? So I'll demonstrate how that works. So first you have to convert this second order ODE to a first order ODE, two first order ODEs. So let y equals y1, and then you can write dy1 by dx equal to y2. So you can convert this equation as, you can write this as dy2 by dx plus e minus x y1 plus sine of y2 equals 0, which can then be written as dy2 by dx equals minus e minus x y1 minus sine y2 excuse me and the first differential equation as mentioned above was this. So these are your two first order ordinary differential equation in terms of y1 and y2 using that you obtained from the second order differential equation. So the first step in shooting method is that we convert the second order ODE to two first order ODEs, right? We know that y1 equals y, so the boundary condition for that is y1 at 1 is equal to 0, but we don't know what y2 at 1 is, right? We don't know that value. Remember, this was a boundary value problem, so we knew the values at the boundaries, but we have converted this now to initial value problems in which we'll start from some initial value and march towards the end or the other boundary. So we know the initial value for y1 because y1 equals y, so y1 at 1 is 0, but we don't know what is y2 at 1, right? We don't know, that value is not given, but we do know this value. So eventually we'll have to reach this value starting with these. So we'll need to guess some value for this and check if we in fact reach this value as we march towards the boundary. So what do we do now? Okay, so let's how are we going to march towards the boundary, right? So the method that we will use for that is called the Euler method. So you can think that there's an analogy between space and time. So we will be marching in this particular problem. We'll be starting with x equals 1, and we'll be marching towards the value at x equals 2, and we will be treating the x dimension as time for this particular problem, right? So using Euler method, when we are marching in time, our I plus 1 will be equal to yi. So let me write this as y1 I plus 1 equals y1 I plus dy1 by dx times delta x, and the second one will be y2i plus 1 equals y2i plus dy2 by dx delta x, right? So if we solve this in a loop starting with the values of y1 and y2, then we should be able to reach the other boundary, yi plus 1 and yi plus y2i plus 1 after certain iterations. That will eventually that will eventually take us to the destination of the other boundary. So when I write this in code, probably it will be clearer to you. So let me implement this in Octave. Okay, so I go to the folder where I have my codes and I edit. Let me open up the editor and write the code as shooting method right. So let's start by writing the equations. Okay, so the first thing that we do is, let me define the x domain, and for the x domain let me specify the interval, so let that be 0.001. okay, and the x, it goes from 1, remember the two ends are 1 to 2, right? So 1 with the interval of dx to 2. Let's count how many elements are there in this, because we'll need that to run the loop. So let that be the number of elements in x. What else do we need? Fine, let's write down these equations. So the derivatives are, let me write this as dy1 dx is equal to, it's a function of y2, and it is, in fact it can be a function of x, y1 and y2. So let's write all of them, x, y1, y2. What it returns is simply y2. That's the first function, right? The second one is dy2 dx, which is also a function of x, y1, y2, and this one returns minus exp minus x times y1, right, minus sine of y2. So we have written these equations, and let's define the initial conditions. Let's define them here itself. So y0, or the first one is, what is it? It was 0, and the last one, it's 0.5. So these are the boundary conditions. These are the derivatives, or ODEs. Let me simply write them as ODEs, right? So we have these defined. Now let's run a loop and implement the Euler's method. So we'll go from 1 to nx. Right, I also need to initialize the values for y. So y is y1, let me initialize it as zeros with nx elements, and y2 is also zeros with nx elements. But we know that y1, y1 of 1 is y1, that's the boundary condition, and y2 of 1 is, we don't know what that is. It is some guess value, right? So we'll have to initialize some guess value also. Let that be 1 for now. Right, now I can implement the Euler method. So y1 of I plus 1 is equal to y1 of I plus dy1 dx of x of I, y1 of I, y2 of I times dx, and the second one is y2 of I plus 1 is equal to y2 of I dy2 of dy2 dx, and the rest all remains the same, right? And now let's plot this t comma x, not t comma x, it's, what is it, it's x comma y1. we'll be plotting y1, right, because that is equal to y. And also hold on, let me also plot the boundary condition, let me check if I'm reaching that value or not. So the boundary condition is x and y and, right? Let me plot that with a marker. Okay, let me open up a tab here itself, Octave and shooting method. So there's an error, it is in line 19. Where is line 19? y1 of 1 is y1. Okay, so yeah, this is some conflicting thing, right? Because y1 I have defined at two places, so this I can write as yi, the initial value, and now it should be fine. Okay, I'm printing again, so I guess I am missing some semicolons somewhere. Yeah, these are the places I'm missing semicolons. There's another error, vectors must match length. So at line 27, column 1. Alright. So x and y1. Okay, so since the loop goes from 1 to nx, and I'm storing values at I plus 1, so you'll have an extra value because you'll have a value stored at nx plus 1. We don't want that because our domain ends at nx, so I'll only run the loop from 1 to nx minus 1, so that when we reach the last one, nx minus 1 plus 1 will be equal to nx. Hopefully there should be no more errors. Yeah, fine. So as you can see, we started with this, we solved our equations. What we did was we took a boundary value problem with the boundary conditions, this one and this one, right? And we solved it with a shooting method with some guess for y2, but we didn't end up at the required boundary condition. So we can change the value of guess and see if we get the correct value. So for 1 we didn't actually reach, so let me try maybe 2. No, it's further going up. So what we can try is, let's see, maybe 0.1 will work. So this is why it's called a shooting method, right? We start with a boundary condition and we shoot by taking different guesses till we reach this. So this doesn't really look, you can reach it after trying multiple values, but it doesn't seem like an efficient way to do it. What you can do is you can make use of something called a function called fzero. So fzero in Octave or MATLAB is a function which gives you the root of an equation. So for example, if you have, let me use this, okay. For example, if you have a function called x squared plus 2x equals 1, if you want to know the root of the function, the way you can do this in MATLAB is best write it as this, write it as a function of x squared plus 2x minus 1, and then use the function called fzero. So let's try that. F0 of the function, which is x square, it's a function of x square plus 2 times x minus 1, and then I need to give it some initial guess. So it gives me the root, or it gives me the value where the function is 0. So at 0.414 the function is 0. So why am I telling you all this? Because we can use this f0 function to come up with our initial guess value. So what we need to do is, we can solve this problem, the shooting thing, we can get this particular solution by the use of this method called, or by the use of the function called Ode45, because that also solves initial value problems, right? And we have converted our boundary value problem to an initial value problem. So we'll be solving that initial value problem using Ode45, right? That's the first thing that we do. Then we take a look at the last value returned by the Ode45 function, right? And then we make a function such that we make a function such that we get the value of the guess, which gives me 0, or which gives me the root, or which gives me the value which is equal to the boundary condition at the end of the domain. So again, this may be all confusing, but let me write it, so probably that will be clear. Let me write it first, how I'm going to implement this. So I'll be creating another file. Let me call it shoot guess.m. So it's a function file. So it returns, let's say, x. The name is shoot guess. What is it taking? It takes in the ODE function, it takes in the initial value, it takes in the guess, and what else? It also takes in tspan or xspan, or whatever you want, and it solves this using Ode45. So you get t comma y Ode45. You remember what Ode45 takes? It takes in your ODE, or the ordinary differential equations. It takes in the tspan, it takes in the initial condition. So I have only one, right? This is the first initial condition, which is equal to the boundary condition, and the second one is the guess, right? And then this function which I'm writing, it will return the final value of the first vector. So when you solve a problem using Ode45, if you have passed in two ordinary differential equations, you'll get in return two columns of y values. The first column corresponds to y1, the second corresponds to y2. So we are interested in the last value of the first column, that of y1. So we take the first column, the last value of the first column. Right. So we have a function now in terms of in terms of these values, in terms of these, which returns x, which is equal to the last value of y1. So let's see how we can use this. So here what I'm going to do is, I'll be writing this ODE fun at x comma y of 2. I'm just copying these two. I'm just making certain syntactic changes. Minus x times y of 1 minus sine of y of 2, right? Minus exp minus y1. Okay, this looks fine. So I'll be using the method called, okay, so I'll be using the fzero function to find the root of the solution of this function, right? So what do? I need the function in terms of x, or in terms of the guess, because I'm solving the function. What I'm doing is I'm finding the root of the function that I pass into f0, and the root corresponds to the guess. So again, look carefully, you'll understand what I mean. So the function that I pass in, I parameterize it in terms of the guess value, because let's just look at this again. This function has many inputs, right? ODE, fun, tspan, init, and guess. But I'm only interested in finding the value of guess for which the function is 0. So I'm going to parameterize this. This is called parameterizing, because I have only passed in one parameter. So I'm going to be parameterizing this function with respect to guess, and then I'll be solving it for the root. So the function itself is it's this, right? This is the function, and I need to solve it where it is 0. So the function needs to be changed slightly. If I subtract this function by the boundary condition at the end, then I'll get the value of the guess for which it is 0. Let me start with some initial guess of 0.1. Okay. There are other things that I need to define. I haven't defined tspan yet. So tspan is nothing but your x value, and init is the y1 value, yi, and guess is guess. Okay. Guess can be anything. guesses what is in fact being solved for in this f0 function. So this returns let me just call it G, and let me comment this out, and let me write this as G. Okay, hopefully this should work. Let me open up a tab again. And let's run shooting method. So as you can see now it works, because with the value of guess G calculated by the f0 function, I was able to shoot for this boundary condition and reach it, and the correct value of guess turned out to be 1.1537. So I hope, let me just go through all of it once again. What I did was I took an second order ordinary differential equation, which was a boundary value problem. I converted that to a initial value problem, which I solved using the Euler method. But for me to solve it using the initial value problem, I didn't have the second initial condition in terms of y2. So I choose some guess value for it, and I see, by solving the initial value problem, I check if I am able to reach the boundary condition specified by the boundary value problem. So I keep on changing the guess values and plotting it and checking if it is actually equal to this value. But instead of guessing all the time, you can use something called the fzero function in MATLAB or Octave. What it does is it finds roots of your given function. So the function that I gave it to find the root of was the Ode45 function itself, a variant of the Ode45 function, in which I am solving the initial value problem and I'm writing a function within a function. So I'm solving the initial value problem using Ode45, and I'm returning the y value, the last value or the end value of the y, as the return of this function. So this particular command f0, it takes in that function and it finds the value of the guess where the function is equal to 0. So my function is this minus y end, right? Because that is where when this equals 0, when this whole thing equals 0, that is the value of my correct guess, right? So that's what f0 finds for me. So that G is stored here, and using that guess now I can correctly reach my boundary condition. Okay, so this may be quite a lot to take in, I think, but if you watch it once or twice, then maybe it will become clearer. So this is how you do your shooting method, and you solve a boundary value problem using initial value problems. So thank you for watching, and I'll see you in the next one.